Yes, good morning. So coming to the next topic of this unit is that is counter. Counter also a sequential circuit. Usually the counter counts the number of clock pulses applied to the digital circuit, and it has many applications in the real world. Okay, so let us see one simple example here, like up counter, down counter in both synchronous and asynchronous operations case. Okay, so here the slide showing a simple 2-bit counter. 2-bit counter. 2-bit counter means it has 4 states. Okay, like 0, 0, 0, 1, 1, 0, 1, 1. So already I think you identified what the slide shows, that is state diagram of the 2-bit counter, state diagram of 2-bit counter. Let assume the state is 0, 0. So in this from this state diagram you can understand the operation is like this. Assume the initial state is 0, 0. If input is 0, it is in the same state, and maintaining the output as 0. Suppose if the input is 1, it goes to the next state, or the count is incremented by 1. Okay, so it goes to the next state and shows the value as 0, 1. Okay, and output is 0. Now the present state is 0, 1. If 0 is the input, it is there in the same state, that is 0, 1, output at 0. Suppose if the input is 1, it changes its state from 0, 1 to 1, 0. Okay, and maintaining output as 0. So now the present state is 1, 0. If the input is 0, it stays in the same state, maintaining the output as 0. Suppose if the input is 1, it goes to the next state, okay, or next count, that is 1, 1. Okay, 1, 1, and showing the output as 1, 0. And present state is now 1, 1. If the input is 0, it maintains same state, otherwise means, suppose if the input is 1, it goes to the initial state, that is 0, 0, showing the output as 1. Okay, so this is the action we can observe in this state table. Okay, this state table, that is a 2-bit counter for the 2-bit counter case. As per this state diagram, that is the action we can observe. Okay, so from this, how to derive or how to construct the logic diagram, how to derive Boolean equations, and finally how to represent the VHDL program for this counter. Okay, so let us prepare a state table for this operation. Let us assume now initially it is a synchronous counter. Okay, so the state table here includes 4 columns. Those are present state, input, next state, output. Present state, input, next state, output. That too, in present state or next state, each state has 2-bit notation. Therefore, in present state and the next state, we have 2 columns again. Q of n, Q1 of n, Q2 of n represents the present state 2 bits. Q1 of n plus 1, Q2 of n plus 2 are the next state 2 bits. Okay, whereas x is the input and y is the output. Okay, so let us fill this truth table. Declare present state input, next state output. So again, in present and next states we have 2 columns. Represent 2 columns because it is a 2-bit counter. Okay, so in each state we have the 2 bits. Q1 of n, Q2 of n represents the present state bits. Q1 of n plus 1, Q2 of n plus 1 represents the next state bits. Okay, first of all, assume the present state is 0, 0. Suppose if the input x is 0, as per this state diagram, the system maintains same state the system maintains same state, that is next state also 0 0, next state also 0 0, and the expected output is 0. Okay, from the table, state diagram what we have seen in the last slide, from based on that we are going to fill this state table. Okay, then suppose if the present state is 0 0, same present state 0 0, suppose if the input is 1, if the input is what happens, it changes its state to the next. Okay, that is 0 0 2, it goes to 0 1 state, 0 1 state, and output is 0, right? Suppose if the present state is 0 0, for input 0 it maintains same state, but for input is 1 it goes to the next state. Okay, now the new state is 0. Okay, right? So now let us assume present state is 0 1, present state is 0 1. For x 0, what will happen? It maintains same state, it maintains the same state 0 1, and output is 0. Suppose if the current state is 0 1 and x value is 1, x value is 1, that is input is 1. Okay, when the input is 1, what happens? It changes its state to the next, that is from 0 1 2 it goes to 1 0, 1 0 state. Okay, 1 0, and output is 0. Okay, similarly present state is 1 0, for 0 input it maintains same state and output is 0, but if the x value is 1, it goes to the next state, that is 1 1, and output is 0. Okay, now the present state is 1 1. Suppose if x is 0, it maintains same state 1 1, the output is 0. Instead of that, if the x value is 1, it goes to the next state. Next state means 0 0. Okay, next state is 0 0, and output maintained as 1. So this is as per the state diagram which I have shown in the previous slide. Okay, based on that this state table is prepared, known as the 2-bit synchronous up counter. Okay, because initially 0 0, then 0 1, next 1 0, next 1. So the count will be increased. The state value is increased from 0 to 3. So you can say this is the up counting action here. Now how to develop this logic diagram for it means, before going to develop the logic diagram, first of all it is better to derive the Boolean equations for y, q1 of n plus 1, q2 of n plus 2. Okay, how to derive? You can take either mapping method, or you can use directly a Boolean algebra. Okay, so for y, since it has only one output value, output 1 at one position only, so corresponding to this, the y equal to q2 of n into q1 of n into x. Okay, that is the equation for y. Similarly, use maps for q2 of n plus 1 and q1 of n plus 1. You may get equations like this. These are the equations for y, q1 of n plus 1, q2 of n plus 1. So with this, the developed diagram is this is the counter, up counter, this is the up counter. Okay, input here is the x. This is a same clock is applied for both the flip-flops, since the designed system is a synchronous model. So same clock is applied for both the flip-flops, and y is the output. The state you can observe here, this is the q2 of n plus 1, and this is the q1 of n plus 1, or you can take n. N represents the present, q2 or q1 of n plus 1 represents the next state. Okay, so like that you can design the logic diagram from the state table through Boolean equations. Okay, and this is the circuit for asynchronous counter. In asynchronous counter case, the clock signal is different for different elements, that is different flip-flops. You observe here, the clock is from the source clock is directly connected to the first D flip-flop, whereas for the second D flip-flop the clock is from the first flip-flop. Okay, it is not directly from the source. And the different feedback connections are there to get the proper outputs. So this is the circuit diagram for asynchronous up counter. Okay. Now let us see the VHDL representation for both these counters. So when you come to VHDL representation, let us take first of all a synchronous counter. While writing the program, first of all you have to write the library IEEE, then use IEEE.standardlogic1164.all, next use IEEE.numericstandard.all. Okay, like the two packages you have to open under this library. One is standard logic 1164 and another one is numeric standard. After that, entity declaration, already we know that it start with the word entity, then entity name is, then port of X in standard logic, clock in standard logic, Q in out, signed off 1 down to 0 and initial value is 0 0, and one more output is Y with the single bit notation standard logic and the value is 0 initially, then end entity name. Okay, so different inputs are X clock, outputs Q Y, but Q is in out mode. It is better to declare in the in out mode. Okay, this is the entity declaration. Then coming to architecture, behavioral of 2-bit synchronous counter is, that is, start with the word architecture, name of entity name is. As per the syntax, these are the names we have to use here. Then architecture begin. After architecture begin, we need to go for process statement because the model is behavioral model. So process of the clock. If proper clock is available, then you need to show up counting. Proper clock means it is a positive triggering. For that purpose, in the process begin, first of all you need to check out if falling edge of the clock. Falling edge means it is not positive triggering, it is negative triggering. Okay, negative triggering. If falling edge of the clock, then after that, suppose if x equal to 1, what happens? It goes to the next state, or the value is incremented by 1, or the state value incremented by 1. Therefore, q of n or q is q plus 1. Q is q plus 1. Like that you can write. The q value is incremented by 1. Suppose if it is 0 0, it goes to 0 1. If it is 0 1, it goes to 1 0. Suppose if it is 1 0, it goes to 1 1. Suppose if it is 1 1, it goes to 0 0. Like that. Okay. So incremented. After that too in the same falling edge. Suppose if the q value is 1 1. If the q value is 1 1, the expected output is 1. Otherwise it is 0. Okay. That also we observed in the state table or state diagram also. If the q value is, if the state is 1 1, okay, after that it moves to, if the state is 1 1, if the q is 1 1, then y is equal to 1, else y equal to 0, and if, is it okay? From 1 1 to when it goes to 0 0, then only y becomes 1, otherwise it is 0. Okay, we will check it. Okay, suppose else means if x value is 0, what will happen? It maintains same state and y value is 0. Okay, so like that you can get the output. So finally end process and architecture name. Okay, so this is the program for up counter. By when x equal to 1, it counts. It increments its value, or it changes its state. Otherwise it maintains same state. Okay, so like that, that is in the, okay, this is the up counter program. In next class we can see down counter, up down counter in the same model, and also VHDL representation for asynchronous up down counters. Okay, for them we can see the programs in the next class. Okay, is it clear? I think with reference to clock signal, how the different operations can be done, because it is a synchronous model. Okay, synchronous model. Okay, in synchronous model, all the actions with reference to the clock will be happened. Okay, thank you.